Have you ever wondered how machines learn? Today, we're diving deep into the fascinating world of deep learning. Deep learning, a subset of machine learning, uses neural networks with many layers, hence deep, to analyze various factors with a structure similar to the human brain. Unlike traditional machine learning, which tackles tasks in a linear manner, deep learning models can handle complex tasks and make decisions with a non-linear approach. Now, what exactly is a neural network? Picture a web of interconnected layers filled with nodes known as neurons. Each neuron receives inputs, performs computations, and generates an output. The magic of deep learning lies in these neurons. The architecture of a neural network is simple. It consists of an input layer, where we feed data, one or more hidden layers where computations occur, and an output layer that delivers the final result. But how does a neuron decide what information to pass on? Here's where the activation function comes in. It decides whether a neuron should be activated or not based on the weighted sum of its inputs. Some popular activation functions are sigmoid, tan, and ReLU. Without an activation function, a neural network would simply be a linear regression model, limiting its ability to handle complex tasks. Training a neural network is a process of adjusting weights and biases. We start with assigning random weights and biases, calculate the error in prediction, and then adjust the weights and biases to minimize this error. This process is known as gradient descent. An optimizer in deep learning speeds up the gradient descent process. It helps find the minimum error quickly and efficiently. Backpropagation, a key part of deep learning, is a method of calculating the gradient of the loss function. It helps adjust the weights and biases, making the model more accurate over time. However, deep learning isn't without challenges. The vanishing gradient problem, where the gradients of the loss function become too small, can slow down learning or cause it to stop entirely. On the other hand, the exploding gradients problem, where the gradients become too large, can lead to unstable and poor performing networks. A neuron in the hidden layer may consistently result in an error due to issues like poor initialization of weights, a bad activation function, or even a learning rate that's too high or too low. In deep learning, computations are represented as graphs. These computational graphs help visualize the operations and understand the flow of data. To measure how well our model is performing, we use a loss function. There are various types, such as mean squared error, cross-entropy, and log loss. Cross-entropy, also known as log loss, is preferred for multi-class classification problems as it penalizes incorrect predictions more heavily. Stochastic gradient descent, or SGD, is a variant of gradient descent. It uses a single randomly chosen data point to update the model parameters, which can cause oscillations towards local minima. Another variant, batch gradient descent, uses the entire dataset to compute the gradient, while mini-batch gradient descent uses a small, random sample. Deciding the batch size in deep learning is a trade-off between computational efficiency and the quality of the gradient estimate. Output, the Hessian, a matrix of second-order partial derivatives, can help speed up training. However, its computation is expensive and impractical for large networks. RMSProp and ADAM are two adaptive learning rate methods. RMSProp adjusts the learning rate for each weight individually, while ADAM goes a step further by combining the perks of RMSProp and momentum-based optimization. ADAM-W, a variant of ADAM, is often preferred as it decouples weight decay and the adaptive learning rate, leading to better training dynamics. Batch normalization and layer normalization help stabilize the learning process and reduce the number of training steps by normalizing the inputs in each layer. Residual connections, on the other hand, allowed the flow of information from earlier layers to later layers, mitigating the vanishing gradient problem. Gradient clipping limits the values of gradients to a small range to prevent the exploding gradients problem. Xavier initialization helps in setting optimal initial weights, promoting better learning. Overfitting, where a model performs well on training data but poorly on unseen data, can be mitigated using techniques like dropout and L1 and L2 regularizations. L1 and L2 regularization owes its name to L1 or first farm and L2 norm or Euclidean norm of a given vector. Dropout randomly ignores neurons during training, reducing the model's reliance on any single neuron and hence preventing overfitting. L1 and L2 regularizations Add a penalty term to the loss function to restrict the complexity of the model. When data explodes with features, deep learning models come to the rescue. Techniques like feature extraction and dimensionality reduction act as data miners, uncovering the key patterns hidden within the vastness, mitigating the curse of dimensionality. Generative models like GANs and VAEs push the boundaries by generating new data instances. GANs pit two networks against each other for realistic outputs, while VAEs sample from the data's core essence to create novel content. Transform your data into a competitive advantage. BigGraph AI empowers you to harness the power of deep learning for real-world results.